Can we always solve AX equals B? Imagine you're an engineer with 9 dials controlling 9 targets. You'd expect to hit any combination of targets. Yeah, but what if one dial secretly duplicates another? Suddenly, there are targets you can never reach, no matter how you turn those dials. This is the difference between a non-singular and a singular matrix. One of the most important ideas in all of linear algebra. Let's make this precise, starting with what A times X equals B really means. A 3 by 3 matrix A has columns a 1, a 2, and a 3. Right? The product A times X equals X1 times a 1 plus X2 times a 2 plus X3 times a 3. This is a linear combination of the columns. You scale each column by a weight, then add them together. Solving AX equals B means finding the weights that combine these columns to hit the target vector B. Let's look at a concrete example. Letter 1 equal the column vector 1, 0, 1. Letter 2 equals 0, 1, 1. And the letter 3 equal 1, 1, 2. Now suppose we choose the weights 2, 3, and 0. We compute 2 times the vector 1, 0, 1, which gives 2, 0, 2. Then 3 times the vector 0, 1, 1, which gives 0, 3, 3. And 0 times the vector 1, 1, 2, which gives 0, 0, 0. Adding these up, we get 2 plus 0 equals 2. 0 plus 3 plus 0 equals 3. And the 2 plus 3 plus 0 equals 5. So the result is the vector 2, 3, 5. The key question is, can every point in three-dimensional space be reached by some combination of these 3 columns? Now consider the opposite scenario. When 3 column vectors point in genuinely different directions, not all lying in the same plane, they are linearly independent. No column can be written as a combination of the others. With independent columns, scaling and combining them sweeps out the entire three-dimensional volume. Every target vector B in R3 is reachable, and AX equals B always has a solution. We call this matrix non-singular or equivalently invertible. The inverse, A inverse, exists, and it gives us the unique solution. X equals A inverse times B. Now see what happens when columns become dependent. Our A3 equals 1, 1, 2, which is exactly a 1 plus a 2. Let's verify. A 1 is 1, 0, 1, and a 2 is 0, 1, 1. Adding them component by component gives 1 plus 0 equals 1, 0 plus 1 equals 1, 1 plus 1 equals 2. That's exactly a 3. So the third column adds nothing new. It lies in the plane spanned by the first 2 vectors. Every combination x1 times a 1 plus x2 times a 2 plus x3 times a 3 reduces to just a combination of a 1 and a 2. Here's why. Since a 3 equals a 1 plus a 2, we can substitute and the whole expression becomes x1 plus x3 times a 1 plus x2 plus x3 times a 2. No matter what weights we choose, the result is trapped in that plane. If our target B is on the plane, great, we can reach it. But a target B off the plane, unreachable, no solution exists. This matrix is singular. It is not invertible. Dependent columns collapse the reachable region from all of three-dimensional space down to a flat plane. That flat plane is the column space. What we just saw was in 3 dimensions, but the same logic holds when dimensions grow large. Consider a 9 by 9 matrix with 9 columns living in 9-dimensional space. If all 9 columns are independent, each one pointing in a genuinely new direction, then their linear combinations fill all of R9. Every vector B is reachable, and the system AX equals B always has a solution. Now suppose column 9 equals column 8. We've lost one independent direction. Instead of 9 independent columns, we only have 8. The combinations now fill only an 8-dimensional subspace sitting inside 9-dimensional space. Infinitely many target vectors lie outside that subspace, permanently unreachable, meaning for those vectors B, the system has no solution. this principle scales identically to any size. Right? In 100 dimensions or 1,000,000, the rule is the same. One dependent column means one lost dimension of reachability, and countless right-hand sides become unsolvable. Singular matrices turn out to be extremely rare. Here's why. Picture two vectors in 3D defining a plane through the origin. For a third vector to create dependence, it must land exactly in that plane, a flat sheet with zero volume in 3D space. A randomly chosen third vector misses that plane with probability 1. The probability of landing in the plane is exactly 0. A random square matrix is almost certainly non-singular. Dependence requires an astronomically unlikely coincidence. Now, one critical clarification: singular does not mean no solutions ever. A singular matrix can solve AX equals B when B lies in the column space, the reachable subspace. It fails for every B outside that subspace. Some B values are reachable, but most are not. The correct way to think about it is singular does not mean no solutions. Singular means not all B are reachable. Let's pull back to the full picture and compare non-singular and singular matrices side by side. A non-singular matrix has independent columns. A singular matrix has dependent columns. At least one column is a combination of the others. For a non-singular matrix, the combinations of its columns fill the entire space Rn. For a singular matrix, those combinations fill only a lower dimensional subspace. This means AX equals B is solvable for every B when the matrix is non-singular, but only for some B when the matrix is singular. And therefore, A inverse exists for a non-singular matrix, and no inverse exists for a singular matrix. And as we discussed, a random matrix is almost certainly non-singular, while being singular is extremely unlikely. Now here is the core logic chain that ties everything together. Independent columns fill Rn. Filling Rn means AX equals B is solvable for all B. Being solvable for all B means the matrix is invertible. Break any link in this chain, make the columns dependent, reduce their coverage of the space, leave some B unreachable, and the matrix becomes singular. This idea, whether the columns fill the space or fall short, connects to rank, to determinants, to eigenvalues. Every major concept in linear algebra circles back to one fundamental question: are the columns independent?